Welcome to Nuclear Physics for Dummies. I'm Mert, and in this series I will walk you through the fascinating world of atomic nucleus, step by step. At its core, nuclear physics is the study of the nucleus, the tiny, dense center of an atom, made of positively charged protons and neutral neutrons, which we collectively call nucleons. Here is a simple drawing of an helium atom which contains 2 protons, 2 neutrons, and 2 electrons around it. This part here is what we call a nucleus. We are interested in 3 big questions. How do these particles interact? How do nuclei change, like when they decay? And how does energy flow in these processes? These questions don't just help us understand atoms, they help us understand everything, from stars and planets to life itself. Our ultimate goal is to understand the origin, evolution, and structure of matter, specifically the ordinary matter that makes up the universe. We call this baryonic matter, and it includes everything you see around you. But the universe has mysteries beyond that, things we won't fully explore in this series, like dark matter, a kind of invisible matter that doesn't emit or absorb light, or dark energy, a mysterious force accelerating the universe's expansion. Fascinating, but for another time. So, how do we even begin to describe nuclei? Think of a nucleus as a self-contained quantum system of fermions, that's protons and neutrons, interacting through incredibly complex forces described by quantum chromodynamics, or QCD. We want to understand how nuclei behave across all scales, from the smallest systems like deuteron, which is just 1 proton and 1 neutron, to giant neutron stars made of nuclear matter. And even beyond that, we want to predict how nuclei behave in unexplored extreme conditions, like in exotic matter or super heavy elements. Okay, let's zoom out and talk about the building blocks of all matter, what physicists called elementary particles. These are the smallest known components of the universe, and they fall into 2 families, fermions and bosons. Fermions are the particles that actually make up matter, like you and me. Examples would include electrons and quarks, which combine to form protons and neutrons. And thanks to something called the Pauli exclusion principle, no 2 identical fermions can occupy the same state at the same time. That's what keeps atoms from collapsing. Bosons, on the other hand, are the force carriers. They are what make particles interact. Some key examples would be photon, carrier of light and electromagnetism. Gluon holds quarks together. W and Z bosons, they're responsible for weak nuclear forces, and the hypothetical graviton, which might carry gravity. Before we forget it, let's add here Pauli exclusion principle. It's worth noting in the 1950s and 60s, physicists thought even protons and neutrons were elementary. Only later did we discover they're actually made of quarks. But you'll still hear the term elementary particles used loosely sometimes. Each elementary particle has unique properties, which we use to tell them apart. Mass, often expressed in energy using Einstein's famous equation E equals mc squared. Charge in units of electric charge. Spin, an eccentric form of angular momentum unique to the quantum world, we could say. So to sum up, nuclear physics is about understanding the heart of matter, how it works, how it changes, and how it powers the universe. Every nucleus is defined by 3 numbers. The atomic number Z is the number of protons. This tells you what element you have. The neutron number N is how many neutrons it contains. And the mass number A is the total number of protons plus neutrons. So A just equals to Z plus N. For example, if we have a carbon-12, which has 6 protons and 6 neutrons, Z would be 6, N would be 6, and A would equal 12. Sometimes you find nuclei of the same element that have different numbers of neutrons. We call these isotopes, like carbon-14, which is radioactive, has 6 protons and 8 neutrons. There are also isobars, which have the same mass number A, but different Z and N. And isotones, which have the same number of neutrons, but different Z and A. These variations are crucial for understanding nuclear stability and reactions. And to summarize, every nucleus is defined by its Z, N, and A. And though it's tiny, it holds enormous secrets, we could say. The nucleus is incredibly small and dense. Its size is measured in femtometers, or 10 to the power of minus 15 meters, also called a Fermi. Most nuclei are between 1 and 7 femtometers across. For example, the radius of a Li-208 nucleus is about 6.8 femtometers. Comparing that to an atom's radius, about 50,000 times larger. We also know that inside the nucleus, the density is roughly constant, about 0.15 nucleons per cubic femtometer, making it one of the densest forms of matter in the universe. How do physicists know all this? By firing high-energy electrons at nuclei and studying how they scatter. From this, we can map the charge distribution and estimate the size and shape. We've even discovered exotic cases like halo nuclei, where a few neutrons form a loose cloud around the core. When it comes to the energy, physicists use the electron volt, or EV for short. 1 electron volt is the energy an electron gains when it moves through a 1 mole potential difference. For nuclear processes, we usually talk in mega electron volts, or 10 to the power of 6 electron volts. For example, the binding energy of a nucleon in a typical nucleus is around 8 mega electron volts. Even higher energies like those in particle physics are in giga electron volts. Time also behaves differently at the nuclear scale. Some nuclei live only 10 to the power of minus 12 seconds, that's a picosecond, while others are stable for billions of years. So we have to think in terms of lifetimes and decay rates rather than ordinary seconds that we know. These units, femtometers, megaelectron volts, picoseconds, match the natural scales of the nucleus. They make the equations simpler, results more meaningful, and experiments are easier to describe. So now you know the nucleus may be small, but it operates on scales of energy and time that are truly extreme. Thank you for watching. If you enjoyed the video, make sure to hit the like button and don't forget to subscribe.